Hey everybody, welcome to PC Perspective. I'm Ryan Shrout, and we are here today with a discussion about Zen processors, microarchitecture, and we're going to get pretty far down into the weeds here in terms of architectural discussion. So much so that I am not afraid to admit that I am the least qualified person on this panel of three that will be joining us to talk about it. First up, we have our very own Josh Walrath joining us.
I'm the second least qualified.
You are indeed the second least qualified person. Everybody knows Josh. And maybe new to some people, for us, is David Kanter. David, you are a, let's see, besides roving tech industry personality, industry consultant specializing in CPU design, performance, that type of thing, out of Real World Technologies. Is URL realworldtech.com for that?
Yep, that's right. And we've got some forums in there. You can go and chime in. And I think one of the things that's sort of interesting about it is it's pretty small, but we've got a fair number of folks who actually design CPUs and GPUs lurking around in there.
Yeah, it's an incredibly interesting place to go. Even if you just want to learn, and if you want to see people on that level having discussions about things, it's pretty compelling. And David also writes for the Microprocessor Report, if you happen to follow some of that. So David has been, I don't know, David's been doing this for I was going to say a decade, but probably more than that, right?
No, I mean, well, it depends. I mean, I'd say, I got real interested in computers in the mid 90s, like when Anand and Tom were all starting out.
Right.
And, I think like many people, I was just really curious. And it ultimately ended up at Real World Tech just because, I think back then, everyone was talking about how AMD was going to be using silicon on insulator. And that was like the one website where I found people could explain the difference between silicon on insulator and bulk, which Intel uses. And I was like, cool, now I can learn about all this stuff. And, I think it took me, so I would say conservatively, I've sure been paying attention and having informed opinions for 10 years, but
Right.
I'd say, it took me 5 years to learn how to just have a reasonably coherent and intelligent opinion.
I would go as far as say more than reasonably. David's work at Real World Tech is where I would go to learn about the microarchitectures that AMD would put out, that NVIDIA would put out, that Intel would put out, so that I could then, siphon it down a level 2 or 3 and kind of communicate with our readers. So it's interesting to see, what different detail levels everybody tends to get into. Josh will go more detailed than I will on process technology. And so it's interesting. That's why I wanted to get this group here to have a discussion about it. Now, the reason we're having the discussion now is we are less than 30 days away from the release of the first Zen-based product, Ryzen desktop processors. That'll happen probably by the end of March or beginning of March, first week of March or so. And also the report that David wrote for the Microprocessor Report is now, I think you wrote it a little while ago, but now it's public.
Yeah.
And Josh and I went through that and we found some, it was an interesting discussion in there that I thought was worth having. So it was actually, Josh's idea to put all this together and kind of have an interesting discussion around it. Now I want to start out basically asking like a high level 10,000 foot question around the claims of 40% IPC improvements, right? That was kind of when AMD first started talking about Zen. It was all about that 40% IPC improvement over their previous architectural designs. And at the time, I don't think it's going on a limb to say that most people thought that was kind of a crazy claim, that to think that any one company, whether it be Intel, AMD, or anybody, would be able to get that much of an improvement in per clock performance seemed far-fetched at best. But everything we have indicated now seems to be that they're doing it. Is that your mindset, and all this is without processors in hand, but do you think they've been able to accomplish that?
Yeah, I mean, so I think when I first heard that, I wouldn't say I was cautiously optimistic, I think is the right way to put it.
Right.
And the bulldozer, steamroller, excavator architecture, frankly, had a lot of pretty fundamental problems baked into it. And I think AMD did a really good job of trying to smooth those over, over the course of 4 or 5 years. But, some of the limitations were just really baked in and difficult to remove. And by the time, you remove them, you know, you might as well start from scratch. And so I think the idea that they could get 40% to me seemed, you know, maybe AMD's track record over the last 5 years wasn't spectacular. So there was
Right.
like a question of execution. But I think, uh, you know, was there enough IPC there to be had? Were there enough improvements? And could I name off what some of them would be? Absolutely. And I think, you know, the interesting question is sort of how far AMD wanted to go down the path of making a huge beefy CPU. And just, I mean, as a corporate level commentary, you know, look, we all know and love AMD. It's a company that has struggled in terms of cash flow,
Sure.
and they just can't throw as many people at a project as Intel can, and they also don't own the process technology anymore. So, you know, I think they had to take an approach that was clever and intelligent and not try to beat Intel head on, because that's just not going to happen anymore. There was a point in time, you know, back when the P4 was out, and this was, you know, I would say before I really had the same level of expertise that I do now. But, you know, the Opteron was a great chip. The Athlon 64 was fantastic. And they kind of caught Intel napping. They saw, you know, a gap in the product. They went for it and they were rewarded. But Intel isn't really screwing around like they used to. At the time, they
Sure.
were holding back x86 to try to help Itanium, and there's none of that anymore.
I
Yeah.
think it's kind of interesting. You know, looking back at Pentium 4, we have seen this before with Intel going from the Pentium 4, which was optimized for high clock speed, but its IPC was not that great. But they didn't care because they could clock it up to 3.2 gigahertz,
Yep.
and then they went to the Core 2. And there was
Yep.
just that huge, massive increase in IPC. They could run the product slower and
Mhm.
still get much better performance than what we saw before. Now AMD had a higher clock speed product with Bulldozer and thinking they could do
Yeah.
the same thing, but obviously not a great idea.
Yeah. Well, and you know, I think you've hit the nail on the head exactly. And there was, and it wasn't just Intel and AMD. If you look at sort of the broader microprocessor landscape, IBM sort of went through this phase as well, and there were a whole bunch of papers out, you know, in the early 2000s talking about, well, what's the best processor we could design? And there were a bunch of people who were talking about 50-stage pipelines. And, you know, if you do a back of the envelope calculation, you know, the stuff we have today is about 20 stages. So, you know, you're talking about people designing processors to hit frequencies that are 1.5 or 2x higher. And, you know, I think quickly what everyone realized is, you know, power wise, that's not sustainable. Number one. Number two, if people buy space heaters, they want to buy space heaters. They don't really want them attached to monitors. And then number three, it's just going to be really hard to design. And frankly, you're better off with 2 cores. Maybe even 4 cores, right? And you know, I think there's an ongoing debate about how many cores is the right
Right.
number, and it's, you know, it's interesting to see in the cell phone, the mobile market, right? There are people who are like, oh, hey, I've got 10, 12 cores, and, you know, Apple, which clearly makes the best phone hardware out there, you know, they're sticking with 2 because,
Yep.
you know, there's a limit to well, especially to my attention span, but generally consumer attention span, and you get 1 or 2 apps.
Sure. What about, so if we do we foresee there being any more jumps of 40% like this in the consumer processor spaces in your mind, right? Obviously, predicting out 5 years or 10 years in processor design is probably impossible to do. But it seems to me, looking at the data that I've seen, that, you know, AMD was able to make this claim and make this jump really only because they had fallen so far behind Intel. And a lot of the architectural improvements and changes and optimizations they've made with Zen in this ground up design are kind of closely falling in line with what Intel has done in their out of order design compared to what they had done previously. Does that seem fair?
Yeah, I mean, I think look, every generation you're able to squeeze out more performance, and, you know, I think generation on generation getting 5-10% IPC is not impossible, but yeah, the only way we'll see something like a 40% IPC improvement is if we start talking about something really crazy and out there, like speculative multi-threading or just really advanced techniques. And to be perfectly honest, a lot of those are, I had a startup doing speculative multi-threading. We talked with Intel, we talked with AMD, we talked with NVIDIA. That stuff is really hard, and it doesn't work in all cases. And, so it's very workload dependent.
Right.
I think, I'm trying to remember who it was, but one of the architects, was giving a talk, and they said, well, why do we like frequency? Well, frequency lifts all boats, right? Every workload that isn't memory bound responds to frequency. But, there's some workloads where, like using AVX 512, is great for some things, but then there's other workloads where it just doesn't really help you because that's not what you're doing.
Sure.
So I think, this 40% is really a one-time improvement, and then it's going to be back to like, sort of performance whack-a-mole, where the things that are holding AMD and Intel back, it's not like there's one real obvious thing. There's 100 or 1,000 small little paper cuts that you've got to just deal with.
Yeah. It's one of the things that we find all the time is in the enthusiast community, the audience tends to complain and gripe about seeing 5 to 7% improvements on Intel's, since Sandy Bridge introduction. That's all we've really had, and it's tough to explain that, like, that's kind of the best anybody can do. And if Intel's not having these huge jumps anymore, the likelihood of anybody else having them would be pretty minimal. And AMD, kind of after this catch-up step, this big leap forward they're making with Zen, we would assume that their subsequent generations would kind of fall into that same pattern. So it'll be interesting to see.
Yeah, I mean, and the other thing is, just in talking about IPC, IPC is important, but I just say it's critically important to just look at performance overall. And I think actually some of the work that you've done is really important. Like, you and Scott Wasson really pioneered thinking about performance in the correct way for gaming, right? Which is, frames per second is lovely, and it's nice, and it's easy for me to comprehend, but that doesn't actually drive user experience, right? And it's frame latency that matters. And so, in that same regard, I'd say, you can talk about IPC till you're blue in the face, but it really matters what the frequency you're running at is, and not just, your base clock and your peak clock, but what's the average clock. And a lot of the improvements there are harder to detect. I think, one of the things you alluded to is when Skylake came out, it was, for enthusiasts, not very impressive, right? And 5 to 8% performance gains, and that was all frequency because Intel, because of their roadmap shifts, they couldn't change the architecture. But if you look at the really power constrained cores, like on those 4 or 6 watt ones, the performance gain is actually very substantial. In some cases, the frequency's up by 15 to 20%.
Yep.
And, that's huge. But, that only helps some people.
Right.
And
mobile specifically, right? Like that, the Skylake design benefited mobile products, whether it be from laptops down to, tablets, in a much more dramatic fashion than it did for desktop users and enthusiast gamers.
That's right. And, the other place where I think we're going to see some real benefits is not just on mobile, but also on servers and just generally like really power constrained environments, right? Because if we look at, a high-end 4-core chip with 65 or 95 watts, basic math, you've got maybe 10 to 20 watts per core. Mm-hmm. So you're not running out of power headroom at all. And your limitation is really, how fast can I run this transistor before it's likely to blow up? On the other hand, when if you look at the rumors for Skylake, say 28 cores, and, you figure 150 watts, all of a sudden you only actually have maybe 4 or 5 watts per core, right? And that's starting to sound a lot more like mobile in some respects.
Yeah. And Josh, feel free to butt in here with any questions. But one of the things I found most interesting, and we'll get into the more of the granular details that Josh has brought up in the document we have, the SMT implementation on Zen is this will be the first time AMD has done that. And you can correct me if I'm wrong there. That's the first time they've had a hyper-threading-like technology. And if anything, Bulldozer was kind of the inverse of that when it came to floating point tech.
CMT.
Yeah. So do we expect the multi-threading capability of these cores to essentially have the same effective performance improvement that we have in Intel's architectures today?
I think we'll have to wait and see. I would expect, so one of the things that's interesting is that it did take Intel a while to get it right. And so Glenn Hinton at Intel was known for quoting around, multi-threading is kind of easy. It's just you need to add in another bit and a mux, right? You just need to know, is it thread 0 or thread 1? And, the real complication there is actually not in designing it in, but it's in validating it and making sure it's correct, right? And, I think back in the day, when it was Jackson technology, right, it was shipping in early versions of the Pentium 4 and was never turned on, probably because there were performance regressions, but also validation. And so I think one of the great things is, now we're talking about 10, 12 years later, there's a lot more experience with it. There's a lot more people who know how to get it up and running. And, I think AMD will benefit from the prior experience. And so their starting point will probably be better than Intel's starting point with the P4.
Well, yeah,
but I wouldn't expect...
Sorry, I'm going to interrupt you here. But with Bulldozer, you still had the same, it was the same shared front end. And so instead of, having just one core behind that, you've got, the decode, fetch, all of that, and it had to figure out which core it was sending the data to. Now it's just, you're using a much more beefier front end, but you're able to interleave instructions probably a little bit more effectively just because they do have that previous experience with CMT.
Yeah, I think that's right. I mean, and look, for Bulldozer, I think it's clear that one of the big weaknesses was the front end, because if you look at it, it could decode 4 instructions per clock, but it's feeding 2 cores. So on average, you got 2 instructions per clock. And, if you look at every single Intel core,
it's a 4 wide.
Yeah, it's been 4 wide for a long time. And admittedly, they have 2 threads, but there wasn't this hard partitioning. And so I think what we'll see is that AMD's SMT implementation won't be quite as robust as Intel's because they just don't have 12 years of experience tuning it, but it'll be pretty good, and they will improve it in subsequent generations, right? I mean, the hard part is getting it in there in the first place, getting it validated, and then you can incrementally tweak it as you go along.
I want to ask, this is more a personal topic that I have. When AMD first kind of announced some of the architectural details publicly about Zen, they included features called Sense MI, included like temperature monitoring, adaptive power control, boost clock, and kind of the controls for that. They talked about neural net prediction and that there was a neural net inside the CPU. Is this like when they were explaining it to me, I was kind of like doing a mental checklist. Like, yeah, okay, I know what that is. Like Intel's processors have had that. Yes, I know what turbo boost is. I know how that works and how that works accurately. I know how branch predictor works. Yes, you can make it better. Is there an artificial intelligence system inside your processor? I don't think so.
You nailed that one.
Is this just a marketing spin on just trying to make their CPU seem more advanced than the competition, I guess?
Yeah. So look, obviously machine learning and neural networks are the hot thing these days.
Yeah.
But
guys, let's beef up the TLB and call it neural net.
Yeah, exactly. No, I mean, this is one of those things where there's a reason I don't work in marketing, and yeah, so there's a couple of different ways to do branch prediction, and actually, if you look at the Jaguar core, that used what's called a perceptron branch predictor, and it is technically a neural network. But it is super, super, super simple because we got to do a branch prediction every single clock cycle. So, we're talking about 4 gigahertz. So you've got, a quarter of a nanosecond to make your prediction. Well, it's true that when I do a Google search, they're also probably running some sort of neural network to figure out what ads to show me. The difference is, they have milliseconds, not fractions of a nanosecond. So, the two things are really very dissimilar. And my suspicion is that what we saw in Zen is that they probably lifted the branch prediction from Jaguar and Bobcat and that line of cores and enhanced it. And yeah, you can call it an artificial neural network, but it's a perceptron-based branch predictor.
Right.
And those have been studied for, at least a decade, maybe more in academia and in industry.
Gotcha. Josh, you want to get into any of the questions you have lined up here?
Yeah, I guess probably the first one is going to be, you had talked about how AMD made decisions in regards to their floating point SIMD AVX unit, and how much die space and power savings do you think that we're really going to see with them kind of cutting it? It's not really cut in half from what Intel's, but it's not nearly as extensive as what Intel offers with the latest generation parts.
Right. So, yeah. So to be clear here, the floating point architecture is actually quite different, right? So one is, as you alluded to, the AVX units in Skylake are 256-bit wide. And so they've got 3 pipelines, 2 that do floating point multiply accumulate, and 1 that does a permute. That's actually not technically floating point. It's really just shuffling bits around. And then they also have a 256-bit load ports and a 256-bit store port. There are other units as well, but those are the critical ones here, right? And AMD made a conscious decision to invest less in AVX, and so instead they have 128-bit wide units, and so each AVX operation will take conceptually 2 cycles to go through. And, I think part of that is a statement by AMD about what they want to focus on. And, I think AVX, AVX2, AVX 512, that's all very, very, very critical for high performance computing and a lot of workloads of that nature. But at the same time, is that really used in Word? Probably not. And so, I think this is part of the AMD trying not to compete with Intel head on, but do something different. And so the other point I'd make about their execution units is AMD has 2 floating point adders and 2 floating point multipliers. So they don't have the sort of conjoined multiply accumulate operation, right? And, obviously for everyone who's familiar with GPUs, all they do is pretty much the floating point multiply accumulate, right? That's
okay. Gotcha.
Right. So, and it's just breaking it apart into separate operations. And there's good reasons to do that. There are advantages and disadvantages of each choice. And, one advantage is you've got more flexibility so that if all I want to do is adds, right, because addition is a more common operation, well, you'll have a slightly, there are some things about that become easier under AMD's design. In terms of power consumption, I don't actually think there's going to be a big difference. The way Intel and everyone else designs their units, if you're not using them, you're going to shut them off. So I don't think that's an issue. I think die space, there is likely to be a difference, right? And it could be, I don't know, anywhere from 0.5 millimeter squared to 1 millimeter squared per core. And actually there was, so I was at ISSCC this week,
Right.
which is the International Solid State Circuits Conference. And there was a presentation from the Zen team talking about the fact that their core is smaller than Skylake. And certainly the smaller vector unit is part of that.
I guess if you were there at the talk, they were very clearly talking about the the core itself, not the entire die, not
Yeah, that's right.
integrating any of the graphic subsystems or something like that that
Yep.
Zen would not have included, right? Okay.
That's right. It was just a statement about let's look at 4 Skylake cores, 8 megabytes of L3 cache with the ring, on Intel side.
Right.
And let's just compare the die area there to the CCX is, I think, what they call it, the core compute complex. But 4 Zen cores in the L3 cache, and the designs there are pretty different. And they also did a more in-depth core-to-core comparison. And yeah, so I mean, it shouldn't be a surprise to anyone that the Zen core is smaller because it's got much narrower floating point units. Now, the one thing I will say is they do have a larger L2 cache, which is pretty cool. So there'll be some workloads where that does help AMD out relative to the Skylake client core.
Gotcha.
Right.
Isn't it kind of interesting how the SRAM seemingly scales between Intel and then what we're assuming Samsung's GlobalFoundries process?
Yeah, well, Intel is there is no one better out there at making SRAM than Intel. And so for those who don't know, right, the way your cache works is, we've got, say, 512 kilobyte cache. Each of those bits is stored in a single SRAM cell. And then, they're all chunked together in a giant array. And then, when I go through, I'll say, oh, give me 64 bytes and let's shuffle that over there. So the SRAM is the basis of your cache. And yeah, Intel's SRAM is amazingly dense. But it could also be, there's sort of a trade-off here of what voltage do I want to run at, and therefore how much power do I burn versus the size. And so, AMD and Intel are making different choices here, and part of that is informed by Intel's, Intel has been better manufacturing, and there's no real question about that. And so they have these incredibly dense, incredibly high performance SRAMs. And you see AMD taking some interesting measures to get some advantages there, right? I think SenseMI, I guess, is the sort of the marketing name, but that is a set of technologies that AMD's developed, and I think we first saw that actually in the Polaris architecture, sort of some predecessors of this, to tune the hardware to take advantage of the dynamic conditions, just like the various facets of Intel's Turbo Boost.
Yeah, indeed.
Moving on to another question. Do you think it's more beneficial in terms of overall design and efficacy to go kind of AMD's way in that, like, take for example their integer execution? I mean, you've got a couple of address generating, and then you've got a couple of the ALUs, I believe. Mm-hmm. Compare and contrast that versus having something that is like 4 pipes that can do all of those things, rather than the two kind of mix and match.
Yeah. So actually the differences between the integer pipelines are not quite as profound. So it's more about the way things are organized. So just to back up, Skylake has 3 address generation units. So when I want to do a load or a store, the first thing that happens is I got to go through, and because it's x86, the address calculations can actually be kind of nasty. So I have a special unit that just does that address calculation. But then importantly, it also is going to do the virtual to physical address translation. And you mentioned the TLB earlier. That's the point of that particular structure. And then I have to go and check, hey, is there another load or store in flight with the same address? Because if someone just wrote to this, then I don't want to check the cache. I want to grab it from that prior operation. So there's a whole bunch of bookkeeping that goes on. And so one of the ways that AMD has a smaller core is they only have 2 address generation units. And, so for workloads where you don't need that third one, now they've saved some area, they maybe saved a little bit of static power, and they saved themselves some design headaches. But, for workloads that are richer in IPC, where you can really sustain, 2 loads in a store per clock, Skylake is going to have a big benefit. So, for example, LinPack, is one of those areas. In scientific computing, you're oftentimes not limited by the calculation part. You're really limited by moving the data around. And so having 2 loads in a store in Skylake will be an advantage over the 2 AGUs in Zen. But, again, going back to what's AMD's goal here, it's not to beat Intel head on. It was a conscious choice to say, hey, we're only going to put 2 of these guys down because we think it's going to save us area and we think it'll allow us to clock better. And on many workloads, we may not see a difference.
Well, kind
So
of
that's
moving
sort of the bet there.
going
right?
back to, oh, sorry, I had to
Yeah,
unmute
no, go
myself.
ahead.
Just looking at their diagrams and talking to the engineers, do you feel that Zen is going to possibly still be a little front end limited, or do you think bottlenecks are going to be elsewhere in the architecture, such as addressing caches, cache performance, or is everything fairly well balanced? And what do you think they said?
It looks to me like a pretty well balanced design. I think a lot of the engineering management and the design process for Zen was a lot more robust and thorough than with Bulldozer. So some of the high level decisions that were made in Bulldozer, I flat out think were bad decisions, like using a write through L1 data cache. And I don't know how thoroughly those were explored at the time. And there were also some personnel changes involved that I don't want to get too into the weeds on. But I think with Zen, it's a really well-balanced architecture from what I can see. And, I think ultimately the question is, well, right, where are the bottlenecks? I think we can look at Skylake and as a comparison and say, yeah, they could get another address generation unit. That's something that they could certainly consider. Like Intel, they have a decoded UOP cache, and that really helps out on the front end. As long as you're operating out of that UOP cache, I think the front end shouldn't be really much of a problem, and you're going to be more limited by, branch prediction is always something that it is good to improve. And then, I think the memory hierarchy, getting data into and out of the caches, the L2 cache, the L3 cache, all that stuff is probably the next place where I'd start looking, I think.
Do you like their decision to go with the exclusive L1, L2, and then use the L3 as a victim cache?
Yeah, I do, actually. So, as context, the Zen caches, the L1 instructions and the L1 data are included in the L2. And so that's great because so I waste about 100 kilobytes of data, or maybe 128K of data out of that L2. But in return, it means that when I'm doing coherency between cores and they're trying to talk to each other, I only need to bother the L2 cache from another core for the most part. And the L1 data cache is just in such a performance critical area that having snoops hit it from other cores is super expensive and really bad news. So I think it's great that the L2 is going to be able to absorb a lot of that core-to-core traffic. And, honestly, making the L3 a victim cache seems like a pretty reasonable thing to do.
Do you want to explain what a victim cache is for?
Oh, yeah, absolutely, right. So in a victim cache, the only way that a line gets into the L3 is if I read it into my L2, and then eventually I'm going and reading some other stuff, and I have to evict that line from the L2, and then it gets stuck into the L3 in case I want it again. In contrast, on the Skylake client core, the L3 cache is inclusive, and that's an 8 megabyte cache, and that includes all the L1s and the L2. And so that is actually very advantageous in a slightly different way. One is that when I shut cores down. All I need to do is take the dirty data, stick it in the L3, and there's no memory traffic, right? So shutting down a core can become quicker as a result of this. That's one. Two is for coherency, all I need to do is check in the L3 cache, and if a line isn't there, then I know it's not in any core on the chip. So, these are different implementation choices, and I think ultimately we'll have to wait for benchmarks and some really specific directed testing to see which one works better. And the other point I'd make is that what works best for client doesn't necessarily work best for server. Right. And so, it's very workload specific. And I think perhaps the best illustration of that is that the way that the coherency works in Knight's Landing, right, which is Intel's, massively multi-core, supercomputer-oriented, GPU alternative, is very, very different than, a Core i7 or a Xeon E5. And again, it's just a reflection of, well, what are you really doing with this? And so I think it'll be very interesting to see where it is that Zen's cache hierarchy excels relative to Intel and where it looks a little bit worse. It has larger L2 caches, so that's great. But there could be challenges in other areas, and we'll just have to wait and see.
I know one of the other questions that Josh had in here that I'm really interested to know your thoughts on is a question about how AMD is achieving these low TDPs compared to estimated comparable performance parts from Intel, in particular like Broadwell E, where they look similar in functionality and performance, but AMD, as if the leaks turn out to be correct, which at this point in this late in the game they probably are, they're going to have an 8-core, 16-thread part at 65 watts, even if it's a couple of hundred megahertz lower than their flagships.
Right. Yeah. Well, so I think there's two things going on here. One is, as we know, like Broadwell E, that's really a server chip. So there are some choices that are made in there that do burn more power, and they provide much more performance when you have like high throughput applications. And I think one of the issues is, as always, what is the workload doing? And for consumers, oftentimes, fewer cores, fewer threads, more cache, more clock speed is a better trade-off. So I think it's going to be really interesting to see how that works. But I think the power and performance benefits, well, really the power benefits that AMD is showing off are pretty darn impressive. The performance, right? I think you and I were both there in San Francisco when they first showed Naples and some Zen stuff when Lisa Su was there, and they had performance numbers, but those were for benchmarks that AMD has chosen.
Right.
And I think ultimately, the trust but verify, I think, is what they say. So, I'm really eager to see, what happens when you and everyone else gets their hands on these chips, because I think that's much more telling than a benchmark that's been selected by a vendor. But I certainly have high hopes for AMD.
Josh?
We could probably. I was originally going to ask you about, if you were a CPU designer, what aspect of Zen would you improve? But you kind of answered that one previous about talking, improvements on branch and TLB, and then maybe look at the cache after that. So we can skip that one. But do you think of any major ideas or design aspects from Bulldozer that may be carried over into this next generation? Something they did that you consider, pretty decent, like the latest excavator models?
No,
it's all crap. Throw it away.
No, not at all. I'm trying to think. So, I mean, obviously, it looks to me like they reused. I mean, they probably reused a lot of the ALUs and integer execution units. Honestly, I
10,000
think,
feet, their floating uh, float unit looks nearly identical to,
right.
what was in one module on Excavator.
Yeah, well, and so I think they might have stuck with that just from a balance standpoint. But if I had to guess, I mean, I don't think that there is a lot that was necessarily carried over. I mean, maybe microcode and some of the ways of handling really complicated instructions, but I think the key, I was at a presentation once where Intel talked about maybe it was Penryn. It was one of the talks where it's supposed to be just a shrink, right? And so we're all told, oh, it's just a shrink. There's no real microarchitecture chain at all. Like it's really just the same core.
Right.
And one of Intel's engineers got up there and said, actually, you might think this is the same, but we had to change 60 to 70% of the design just
Huh.
to a new process and take advantage of it. And so, and I think looking at 28 nanometer with planar transistors and high K metal gates versus 14 nanometers with FinFETs, that's such a huge change that I think my guess is that the team at AMD looked at everything in Bulldozer and says, okay, these are some building blocks we can call on, but we need to reevaluate almost every single decision we've
Yeah,
made.
it's going to pretty much essentially be clean sheet from that point on once they get a high level, flow going.
Yeah. And, I mean, look, you engineers are by definition lazy because it's about doing the most with the least. And so where they have perfectly functional pieces of bulldozer or excavator and steamroller, they're going to continue to use those. So like the dynamic voltage and frequency scaling system that's in Zen, that is an evolution of an enhanced version of what is in the CPU side from steamroller and excavator. And that's also shared with the GPU guys, right? And I think one of the things that we're seeing at AMD is, there's more convergence on how do we look at the SoC as a collection of different building blocks, whether that's in video encode, video decode, GPU, CPU, in a really unified and holistic way. And so I'm sure they drew on a bunch of that stuff as well.
Hmm. I'm looking through the rest of our notes here, and one of the I want to end on a couple of interesting things. One, since the split of AMD into its processor division, away from the manufacturing side, I've always been very curious when that would actually start to affect them in any kind of significant way. Do you think the separation of the design side from the process side with Zen has had any kind of disadvantage or even potentially advantage on the architectural design itself?
So basically, he's asking, should real men have fabs?
Exactly.
So the truth is, owning the fab makes life a heck of a lot easier.
Yeah.
And there's some things that you can't do unless you have tight control over the fab. And it's not that it's impossible for AMD, it's just it takes them a bit longer to get around to it, and their fab partners may not be willing to handle it.
So it's kind of like I hire a tailor 24 hours a day, and whenever I want clothes, I can get it to my exact specifications, as compared to what they're doing now is I'm shopping at Kmart, and if I find something on the shelf that kind of fits, that's what I got to buy.
Well, it's sort of true, except I think you've got the relationship backwards for Intel. When you're at Intel and you're a designer, you do not tell the fab people what to do. The fab people will tell you what you can and cannot do. So no, and I mean this is really true. Like some of these talks they had like analog circuit designers, like the guys who work on like PCI Express and clocking circuits, talking about it's really hard to work in a cutting edge, like super cutting edge process that's optimized for digital, and it's true. So I think so to answer your question a little bit more directly, AMD has spent a lot of time evolving to be in a comfortable fabless state. And, we saw that with 28 nanometer high-K metal gate. They moved away from silicon on insulator, which does give a slight performance advantage, and they were able to keep their frequency the same. So like that took some serious circuit design effort and buckling down to make that happen. And I think when I was at the Zen talk at ISSCC, there was a lot of emphasis on how do we use design tools to automate things? How do we make a standard fab flow really work for us? And so AMD has invested a lot of effort into that area. But at the same time, like, it's not like, I think the Kmart analogy is not apt. So one example of something that AMD did that they talked about that was pretty cool is they designed a custom capacitor for their chip. And so, well, why do you want a custom capacitor? And so the answer is when I start changing my workload. So let's say, I load up Witcher 3. All of a sudden, these cores go from sleep to full throttle, like, in microseconds or milliseconds. And if you've ever been through a brownout, that can actually cause something like a brownout, but just on your chip, right? Which is you've got all of a sudden I'm cranking up these cores, they're sucking down so much power that it sort of steals from everyone else. And so one of the ways that you can handle this is by having a lot of capacitors nearby, right? And so all of a sudden, that sort of power surge just draws on the capacitors. And so, AMD went in, worked with Global Foundries, designed a custom capacitor, and about 40 to 45% of the CPU cores and caches are sort of covered in these capacitors to allow better dynamic voltage and frequency scaling, higher clock frequencies. So, I think AMD is taking a targeted approach to how do I get the best of both worlds. On the other hand, some of the stuff that Intel's fab guys have done is just nothing short of miraculous. They have these incredibly thick upper level metal layers. They have air gap dielectrics on their 14 nanometer process. I mean, there's just, for someone like me, it's just a really exciting time because everyone is having to look for so many different tools to get a bit more performance. And, AMD and Intel are just totally different companies. And so they look at problems differently. And, Intel, they control the fab. So they start thinking about, well, how can we manufacture our way out of this? What can we do with process technology? What can we do with custom packaging? And AMD, they have to work with partners, and they have to think about, well, we can't be too aggressive, or Global Foundries is not going to be able to deliver what we want to do, right? And so I think one of AMD's real strengths as a company is that they're very cognizant of what is feasible in high volume. And I think actually in graphics, there's sort of a better illustration of this, which is, from my perspective, NVIDIA goes out and they will build the biggest, baddest GPU. They build the product that they want to buy. And then sometimes the manufacturing supply chain just comes up short and you can't find any HBM2 in high volume. You can't yield your chip out because it's gigantic. And your availability suffers. And on the other hand, AMD has for a long time had like the sweet spot strategy, right? Where, they try to go with things that are smaller. And yes, did they use HBM? Absolutely in Fiji, but, Fiji was never supposed to be a particularly high volume part. And that was, I think in many respects, a learning vehicle.
Right.
Yeah, I think the Fermi versus the HD 5000 series is a really good example of that. AMD kind of worked in what would work best, what could they ship most without being overly aggressive, while NVIDIA kind of shot for the moon with the GTX 480, and they kind of paid a price.
Yeah, that's right. And there's no, both approaches have advantages, right? And, I think part of it is like, if you look at the high-end Pascal, that wasn't ever really meant for consumers. That's meant for supercomputer guys. And, you're talking about a different price range, a different set of targets. And I'm sure there are people who spend $800 on a GPU. I just don't know many of them. Like I think, right, most of them are in 250 to 500, and that's really what you got to aim for.
Yep.
But these HPC guys, they don't bat an eye at spending $1, $2, $3,000 on a GPU, and so the right choice for a $3,000 chip is just very different than a $250 chip. And you can see this with Intel too. The first chips that Intel always releases on a new process are always very small, like 80 to 150 millimeters squared. And it's not till they've been up and running for 6 to 12 months that they start trying to squeeze out, 500 millimeter squared behemoths, because the yields just won't work.
Right.
And so, you can skate ahead of the puck and say, look, we're damn the consequences. I'm going to make a big chip. And, sooner or later my fab will catch up. It just means you're going to have a rocky, 6 to 12 months with your supply chain.
Right. I want to kind of round up this discussion. I feel like this has been a great discussion, but I think maybe we should do this again after we have our hands on Zen parts and Ryzen processors. We can actually measure some of these performance levels. But if you had to, looking at the data and information that you have now here, just a month from the release of these products, if you had to compare the single-threaded and multi-threaded performance of what Zen is to what Skylake and Kaby Lake is, where does it have an advantage or a disadvantage, do you think?
Right. So clearly, if you have a workload that'll scale to 8 cores, I think you're going to find that Zen is going to be fantastic compared to the the Core i7 7770K. Did I get that right?
7700K.
100K.
Yes, sorry,
Yeah.
7700K. I had one too many sevens. Oh boy. Yeah. So, look, if you can use more cores is always a great way to go. And so I think there is a potential for AMD having an advantage there. However, my personal belief is that for consumer workloads, the thing that really matters is, per thread performance for like 1 or 2 threads. And the other thing I'd also say is just keeping in mind time frame, right? So, I think you laid down the stakes pretty well, right? We've got Kaby Lake is out right now. Zen's going to be out sometime first quarter of this year, say March. Later this year, we have Skylake server coming out, and that means that the Skylake E for enthusiasts is also coming out. So, and there's a lot that we don't know about that, so that's a really tough comparison to make. But I'd say, what I see so far is Kaby Lake is going to have better per core performance, probably some higher clocks. But the goal for AMD is not to beat Intel head on, it's to get close enough and then, try and shine in a couple different areas. And I think, having more cores is one way you can do that.
Yeah.
Maybe higher performance integrated graphics, although that is a very tough thing to do because of Intel's Crystalwell, right? The embedded DRAM that they have gives their GPUs, a really nice boost.
Yep.
But so I my expectation is, and I think I said this in the article, is if you look at a high level at Zen and you squint real hard, it kind of looks like something that's a little bit in between Ivy Bridge and Haswell, right? It doesn't have the AVX beefiness and
Right.
vector units of Haswell, but on the integer side, it does look kind of similar. It's got that decoded UOP cache, it's got multi-threading, it's got plenty of ALUs, and so a lot of this is going to come down to what's the implementation and how can they clock it.
Mm-hmm.
And by the way, how they can clock it is going to change over time.
Sure. Yeah.
I think we saw at Intel, The Xeon E5 2699A is the same as the 2699, except it's 200 megahertz faster and probably costs like $1,000 more. No,
Of course,
right.
yes.
But they were able to squeeze that out because they had run so much more volume on 14 nanometer, and the process itself was better characterized. Like, one of the things that I think is very much hidden from view is on all this cutting edge digital stuff. There's no such thing as digital transistors and analog transistors. There are only analog transistors and analog transistors that you treat as digital because it's very convenient and easy to do so. And so as you understand the analog characteristics of your transistors better, you can really understand the inner workings a little bit better. And you get that through driving more volume through your fab,
right.
And also having your design teams like really sort of start studying, okay, this is what we expect. This is what we got. Let's compare, contrast, adjust our models, keep on iterating. And, as Moore's law stretches out, we're going to see a lot more of that, right?
Yeah.
So
Design's really going to be coming to the fore as process nodes stretch out to take longer, for
right.
manufacturers to take advantage of the inherent improvements of the smaller process.
That's right.
Why did that take so long for me to explain?
Words are hard.
Yeah, but it's all good. And the other thing is it's about providing consistent improvement, right? I think just generally as a PC enthusiast, right? I understood why Intel skipped Broadwell on the desktop for the most part, right? It wasn't a part that was designed to have a lot of high ROI. There weren't a lot of features. And, I think they learned a very expensive lesson that it's important to always have an upgrade every year. And this is not lost on AMD either. And so I think, we're just going to see them stretching for more and more different things in terms of how they get that in a more mature process as part of that. For Intel chose to go with 4K and HDR. And so I'm excited to see how Zen turns out. I'm excited to see the performance numbers. And then, I'm also excited to see how they're going to tweak things in the future because, they know they can't sit still.
Right. Yeah. Well, David, I don't want to keep you any longer. I want to thank you tremendously for coming on and doing this little interview and discussion. If you're up for it, I do think this would maybe be more interesting to conclude in sometime in March after we have processors out and performance out, and we can talk a little bit about how all the features that you've talked about and analyzed were actually implemented and how it actually turns out in terms of performance numbers and software. And then we can get out into the discussion about pricing as well and whether or not AMD has made good decisions in that realm as well. So.
Oh yeah. I mean, that would be really fun. I mean, there would be an awful lot more
things
material
to talk about.
Yeah. I mean, who knows? We might all be using Zen-based PCs by then.
We probably all be converted over globally across the world. So obviously, you know where to find Josh and I. We're at PCPer.com, and we do our podcast every week on Wednesday nights. You can find David Kanter over at realworldtech.com, which is where you still post articles and news stories and stuff there, in addition to some of the consulting stuff you do, right?
That's right. It's probably, I'm posting maybe, once a quarter or so.
Yeah.
You can also find me on Twitter. My handle is the Kanter.
Well done.
Yeah, I think
you have an alter ego
David
named
was
the
taken,
Can?
and I think Kanter was taken, and I'm like, well, I guess I'm the Kanter now.
When your name is just taken, you have to make some tough decisions. I don't doubt it. But thank you very much for joining us. If anybody wants to find more information, like I said, go to realworldtech.com, follow them on Twitter, go through those forums. The Microprocessor Report is a great place for information if you need it to that type of degree. Otherwise, we'll have our review up on Ryzen processors. I guess I can't say exactly when precisely, but relatively soon by the time you're watching this. So stay tuned. Thanks, everyone.
Yeah. See you guys in San Francisco.
That's right. If you enjoyed this content, consider supporting in-depth technical content by contributing at patreon.com/PCPer.